All right. Welcome back to day 3, or welcome to day 3, data structures. First things first, I'm going to introduce Ben, who is who is going to talk to you about Tufts Engineering Mentors, which is kind of a cool process for any of you guys who want to be engineers and otherwise, I hear, like other CS majors, and I will not steal Ben's thunder, but he's going to talk about a little bit about this, and here's the details about that. And he will chat about it and then hand out a little set of cards, unless you already did, about that. All right, over to you, Ben.
All right. So Tufts Engineering Mentors is a group for engineering students and CS majors in the liberal arts school. So we pair underclassmen with upperclassmen to get a mentorship relation going on. So with this relationship, you can get, if you have questions about classwork, if you have questions about which classes to take, if you have questions about internships, interviews, resumes, you can ask your mentor, and ideally mentees can also help their mentors, but you can see that if you try it out. We also host other events where we have speakers from high-level companies come and give speeches on their experience with mentorship and engineering in general. So last year we had the CEO, some high-level executives from Milwaukee Tools, from Bose, so they came and spoke, and they were very interesting speeches from my perspective. So this upcoming week, next Wednesday, we're holding a mentee speed dating, which means that if you want to sign up for the club, you can actually meet your first mentor. So we're having mentors and mentees pair up, and we're trying to find the best fit for people.
You don't actually have to date your mentor.
Yes, that is definitely not a requirement. So that is next Wednesday, 9/17, and it will be in DeWitt. You can find out more information online at our Facebook page, which is Facebook Tufts Engineering Mentors. And also, if you plan on coming as a mentee, we would like you to sign up a form online, and you can find that at the link on the board. And actually, do we have any juniors and seniors in the class? Okay, so you guys would be mentors, so there's actually a little bit more of an application process if you're interested. It's the same link as that instead of mentee, it's mentor. So we would very much like to have junior and senior mentors, so I hope you apply. And I am also going to hand out these sheets of paper just to get emails if you're interested about getting on our e-list for more information. So.
Do you want them to fill those out now?
You can fill them out whenever, and I will be in the back after class.
Okay, awesome. Anybody have any questions for Ben about mentors? I think this is a great opportunity, especially if you younger folks who are new to Tufts and like wanting to kind of figure out how to become engineers or in your major, et cetera. This is a really great opportunity, so don't let it go by.
All right, thanks.
Thanks, guys. Or thanks, Ben. All right. Thanks, Ben. All right. Labs finished up yesterday, or started Monday and yesterday. If for some reason you didn't go to your lab or aren't signed up or something like that, you should probably see me, or at least email me about that. Was the lab all right? Yay or nay? It's okay. I see a couple people going, it was all right. Most people said when I went around, I tried to go to all the labs except I missed one because I had to teach another class. So if you were in the 4:30 class yesterday, you probably didn't see me, and I apologize. I'll try to get there at some point. But I just wanted to kind of start to know some of you guys. And the big thing I got was, for those of you who took Comp 11, you said, oh, I'm still a little bit rusty in C++. Is that about right? Yeah, it takes a couple weeks to get back up to speed in this language, especially in any programming language, really. But hopefully yesterday's lab wasn't too painful, and you were able to get at least most of it done, if not a completed lab. Would people be interested in me sending out a solution to the lab for those who didn't get it? Okay, yes. Somebody, you who are nodding your head, what's your name again? Dan, please email me and say, post the solution to lab 1. Thank you. Okay, what questions do you have at this point?
Well,
yeah, Ben.
this isn't too off the mark.
Uh-huh.
I'm a bit confused as to how headers and bodies work. That's a new concept. Headers in terms of the header file, .h file? Okay, oh, that reminds me.
tomorrow's Thursday. Thursday night, I'm planning on doing a C++ kind of overview class. I haven't decided exactly when it's going to be yet, probably around 8 p.m. or something like that. Ben, could you email me and say, remind me to post a Piazza post, okay, about that? It'll be me and a TA, and we'll go over some C++ things and answer all those kinds of questions. But the bottom line is, the header file just lists functions in general, for the most part, okay? Yes, Murata.
We know we're probably not going to be free tomorrow. Would that be videotaped?
I will videotape it. Write me an email and say videotape it. I'm just not going to remember all this stuff if you guys don't email me. And I will certainly videotape it. I don't know how helpful the videotape will be, but I'll do what I can on that. OK. Does anybody else have any questions on that part? OK, for those of you who are still not registered in ISIS, hopefully you got an email from me today saying that you now have the ability to go onto ISIS and register. I saw some people were successful. Was anybody not successful doing that? OK, those of you who were not successful, either you didn't fill in the form at the first day or some other thing went wrong. So you guys email me or stop after class and we'll try to figure it out, OK? For everybody else, you're either registered or you got the email and you tried registering or you haven't yet and you will. And then we should be good to go. There's 160 or 161 people all together in both sections. So it's a fair amount of people, but we are letting everybody in at this point. So that's good. OK, any other questions at this point? Yes?
Do we have to have a README file for the assignment?
Say again?
The README file, do we have to actually put the...
You have to have a README file. There is one that's provided for you in the assignment. You have to modify that according to what we ask for in the assignment. That's all. Yep. Yeah. Alex. The lab did not have a README. Nope. No, Miranda?
Do we keep in all of your comments that you put into the code?
You can keep all my comments in this assignment, yeah.
Same
Yeah.
with the README?
With the README, no, you should kind of pretty much redo the README. As just follow what it says in the README to actually do.
Okay.
The README is just a template in that sense. OK, good. Yep.
I think this was asked earlier, but I forgot the answer. Do you want us to comment also, or just?
Do I want you to comment also? You do not have to do extensive comments. There might be one or two places where you can, and we're not going to like take points off for like no extra comments in this one. For other assignments, we'll give you basically part of your grade be based on whether or not you did good appropriate commenting. Remember, every line should not be commented. Big ideas get commented. The whys get commented, that sort of thing. But no, in this case, most of it's commented for you for this assignment. Yeah. OK. Yeah.
Aside from the README, we don't have to do any documentation or anything.
Aside from the README, you don't have to do any other explicit documentation. No. Did you in other classes you've been in?
Yeah. In high school, we had to do Java docs.
Oh, Java docs. No. No, you do not have to do the equivalent, which I don't even know what the equivalent are for C++ docs. Although we'll talk about man files in a second, and that's in some sense what you could produce if you wanted to. I don't exactly know how, but you could. All right. Anything else? Great. Today, we're going to talk about this thing called asymptotic analysis. Now, in previous iterations of this class, we've kind of waited for a while to get into this, but I wanted to give you I wanted to kind of start out very early thinking about this topic so that every data structure we get to, you start thinking about the overall long-term runtime of your programs and be able to compare them to other data structures. Okay? This is a little bit mathy. There's one particular math slide in here that those of you who hate math should just cover your eyes a little bit and not worry about, because I'm not going to test you on it. Other than that, when you take, if the math part is too little for you, you can certainly look up lots of this stuff online. There's pages and pages on it all over the place. But you also should consider taking algorithms class and then also computational complexity, or I think it's theory of computation class in a couple semesters or next year or 2 years or something, because those go into super duper details. We are just going to touch the surface of this analysis just so that you can basically make the decisions we talked about on the first couple days about whether your programs whether the data structures you choose are appropriate for the situation. Okay, so I wanted to get that out of the way, and that's what we're going to talk about today. Just a couple brief things at first. We're going to do a little quick Unix tip of the day, and then the Eclipse tip of the day. I wanted to show you a little bit of how you go about doing debugging in Eclipse. Okay, if you watch the the Homework 0 video. You saw a little bit of that, but I'm going to review a little bit of that too and just show you a couple of things that you can do with the debugging. So if you do want to use Eclipse, you can have a debugger kind of right there for you. And I think some of you will go, wow, this is cool. All right, then I'll show you a little obfuscated C, which I mentioned the other day, which is what your program should not be. This is a do as I say, not as I do in this sense. And then we'll go over the asymptotic behavior. OK? All right, first things first. If you are in Unix and you have no idea how to use a command, OK, or in some cases if you don't know what command to use, there is another command called man, and it stands for manual. OK, and what you do is you type man, a space, and then the name of the command. So let me show you. That's not what I wanted to show you. There we go. Let me go into the, oops, hang on. Am I not connected to the network? I'm not. Hold on. Tufts doesn't really matter that much. Oh, it will when I do the Eclipse. Hold on. All right, let's try this again. What you're going to do is you're going to type man and then the name of the command, like for instance, ls. OK, so now we are connected. OK, man ls. OK, what will come up is the name of the command and then a description of the command and then every single flag that the command has. And as I'm scrolling down here, ls has a ton of flags that it has available to it, right? If you want to, let's see, what are some that I've used before? I use reverse sometimes, right? -R reverses the list. So if you get a list of files and just for whatever reason you want them in the reverse order, let's say you're ordering them by time, right? And I think T is another one down here. There we go. No, it's not. There it is. Sort by modification time. So if you want to see, you have a long list of files in your folder and you want to see what the first one, or the most recently modified file is, ls-t will do that for you. OK? So let's take a look. If I do ls in my directory, I've got a zillion files here, right? If I do ls-al, or I guess it's just do l, ls-l gives you a list of all the files with extra information. And if I do ls-lt, it will notice this one was changed in 2008 when I wasn't even at Tufts, so I'm not sure how that happened. But probably when I copied it in somehow, right? And then the ones up here were most recently like September, et cetera. OK? So you see how that works? A lot of times, one of the ones I use all the time is ls-alrt. A meaning all files, show me the hidden ones too. L meaning this nice list format. R meaning reverse the list because T means time. So what I do this case, the last file, it said, oh look, my .git config file happened to be modified today at 1:41. So like 2 minutes ago, somebody was fooling around my git config file. I have no idea why. All right? I mean, I don't know exactly know why it does that. Somebody just hacked into my computer, obviously. So anyway, but the point is that man will give you that. If you want to know what the command cp for copy looks like, man cp, right? And that's how you get a lot of different information. It's all there. Yes?
What happens when you
man tells you what the manual file is. It says man, format and display the online manual pages. All right? Yeah. You can do that, of course. OK? If you don't necessarily know what command you're looking for, and this is a little hit and miss, man and then -k, and then let's say I wanted to do copy, right? Man-k prints out everything that has copy in there somewhere. And you sometimes can find out, this one's a little long, this list. But the man-k will give you a context available, even though k doesn't stand for context. But it will tell you some context. Yeah?
You can get out of all these screens with Q.
Yeah, sorry. All the screens you get out with typing Q in this case. OK? One time I had a friend who, Google has, sometimes you can type man and then the name into the Google search engine. And just because people type man, Google sometimes brings up a page. So some people use that as their man instead of the terminal for whatever reason. One of my friends was looking up the absolute value function. And so she went to Google and typed man abs. And she got all these links that she was not expecting. Right? Was not the ones that she was expecting. OK, that's the man command. All right. Let's see. Is there anything else? Oops. Anything else on this one? Man. OK. Eclipse tip of the day. Let me see if I can get this to work. I'm going to try to do this as if you were at home. I'm going to Tufts Homework X. I have a little command that does. I'm going to have to bring this down too. Hang on. All right. OK. And yeah, question, Moreno.
How did you get into the homework server without like the long?
I created a function. If you look up how to do Unix functions, you can put that in your .bash_rc or .bash_rc file, and it does it. So I can maybe do a Unix tip of the day on that sometime too. But anyway, it does make it nicer so you don't have to type all that stuff. And I also did it so you don't have to do a password, which is kind of fun too. OK, so Eclipse is coming up, and my default. And let's hope that this isn't too slow. Looks pretty good. Most people used Eclipse in lab. Positive, negative. It's OK. Come positives, OK. Again, if you don't like it, if you hate it, no worries. Yes, Maria?
So I had an issue in lab where it wouldn't compile. I had to compile to the terminal.
Did you start a project?
Yes.
OK. Well, we can take a look at it next lab if you want. But if sometimes that happens. Sometimes you have to click on the actual project name, like up here. Click on the project name, and then it will then build. But sometimes it doesn't. Yep.
If you update the file using a different text editor or whatever,
Yep.
and you basically save that to the homework server, will it update in Eclipse as well?
It will. If you update the file in a different text editor, it will update it in Eclipse. You sometimes have to do file refresh to do that. Sometimes you have to do that. OK? All right, so here's what I did. I put in, this is your hookbook code. Hopefully the text is big enough to read. This is the hookbook code. And in here you had to do the add friend. And some of you guys, I might actually say lots of you guys, decided that you didn't care to check for the friend list being null. Anybody do that? They crashed, right? You forgot to do that. So I just commented out the part in this that says where the friend list is null. And if I go and run this, right, it should come up, and it compiles it, and then it says terminated, right? And you get no output. Terminated in Eclipse language in this case basically means your program just crashed. It could be a seg fault, it could be something else, but it just basically crashed, right? Terminated means did not go to completion. Okay, and you go and you scratch your head and you say, I have no idea what's going on here, right? And you look at your add friend method, and you say, OK, maybe you say, I'm sure that this part works. I've found the friend properly. What you can do is you can say, oh, how about if I want to run the program so that it stops right on this line. And I'm going to analyze the program stopped at this line. I'm going to see what's going on. If you double click right there, it puts a little dot, and then you go, oh, OK, now I'm going to debug it. Nice, they made this icon into a little bug, right? And then it goes into, and it says, do you want to go into the debug perspective? Yes, and you want to hit remember probably. And then it starts to, hopefully, debug your program. And what it normally does is goes to the first line and stops and goes, what do you want to do? All right, there. And let me see, did it do that? Did I just click on something I shouldn't have? Hang on. Oh, there it is. OK. Let me go back down here a little bit. All right, it stopped on the line, the first line. This button up here says resume, which means keep going until you hit my little point that I stopped, which was a breakpoint. Now, it's going to do that. And guess what? It stopped right in this line. And it says, now what do you want to do? Well, what I want to do is I want to look at some of this stuff. Let's look at my index. If I hover over there, it says the index is 1 right now. Woohoo! Right? It tells me the index is 1. OK, well, let's look at HBook. Well, that's some interesting stuff, right? And it tells us stuff. So you can just hover over it and look, which is awesome. It tells you exactly what's going on in the program. Yeah?
Do you hover over the blue variable?
Yeah, in this case, I hovered over like index for the index variable, and it tells me that. Now, up here, there's a little screen. I'm going to make this a little bit bigger so you can see it. There's a little screen up here that tells us about the whole state of the program, right? So member ID happens to be 1 right now. Our friend ID is 0. Our index is 1, et cetera. So it's all the details. This is the thing that, and by this I mean like the variable this. It's not really a variable. The state this is for the class itself. If you click on the little arrow there, no, it didn't just die. Hold on. Oh, no, it just died. Oh, it did. It just died. Oh my gosh. Sorry. You know what I'm going to have to do? I'm going to have to kill it, I bet. So what I was about to show you was that that little part gives you all the data, including, like, for instance, the hook book, the H book array, and you can actually see all the little pirates in there. Well, they don't look like pirates. They just look like code, right? But you can see that in there. And let me try this again. Let's see if I can just do this and if it'll get back to where we are. If you ever teach and you have something go wrong in class, you got to learn to, like, recover. I'm terrible at it. Anyway, okay. So, all right, here we go. So this, all right, shows you that we're talking about a pirate star, which is a pointer to the pirate array. Well, the fact that it's a pointer, the Eclipse at this point doesn't really know more than it's a pointer. Remember, it's an array. So what you can actually do is you can right-click on this, and you can go down and say Display as Array. And it asks you, it says, what's the start index? It's generally going to be 0. Let's say there's 12. It says a length of 12. Let's say there's 12 pirates. There happen to be, but you could put whatever you want in there. And then it will say, oh, now I know it's an array, right? And then it says, hey, look, it's a pirate array of 12. Awesome, right? And you can say, if I click there, hey, there's pirate 0, and there's pirate 1, and there's pirate 2. And we happen to be working on pirate 1 right now. And if we analyze it, we can say, oh, the member ID is 1. And the name is, well, it doesn't tell you right there, but you can probably click and get to the name. It's a little harder to do because it's a string. But then you can say, OK, the friend list is an int pointer, which is an array pointer. And what's its value? Null. And if you've got a null pointer, you can't reference all of the items in it, right? So this, if you got to this point, you go, oh, my friend list is null. I get it, right? And I don't expect you to necessarily be able to do all those logic steps quite yet. But this is just showing you kind of how you might do that. You get to the friend list, you say, oh, it's null. I have to go back and check for that. Yeah?
When the value of the pointer is null, does that mean the pointer is not pointing to anything, or the address it's pointing to has nothing?
Good question. It means that if the address, or if the value is null and it's a pointer, that means that the address is 0. And nothing can have an address of 0 in a program. Like, an address of 0 means that address does not exist. I mean, it really does. It's an address 0, but you can't do anything with it. If you try to do anything with it, the program says, you're trying to access memory that you shouldn't be, goodbye, and just crashes. OK? Yeah?
If you want to insert a breakpoint for like a for loop,
yeah.
To stop on each iteration, do you do anything differently?
Nope. If you want to look at a for loop, so let's do that. If you want to look at a for loop, let me stop this. Let me fix my code. And let's see. By fixing the code, I'm going to go up, and there it is. I'm going to make sure I check for the null. So, OK, so there's a loop right here. Do you want it to stop at the beginning of each iteration? OK, if you do it at the beginning of each, you could do a couple things. You could do the breakpoint right at the beginning, the first line inside the loop. Or you could do it at the outside of the loop, because every time, the for loop does get executed every time you go through. So either one would work fine. OK? Yeah?
Does that stop it before it runs the line you double-clicked on, or after?
Before. It stops it before the line. So then you have to click. Oh, and by the way, if you want to go one line at a time, I don't have it on here. The debug, that's not highlighted here. Let me just debug, and we'll get there. Let's see. OK. And for those of you using Xcode, very similar tools on here. I'd be happy to sit down with you and show you the same tools for Xcode. Visual Studio, same thing. There's most debuggers are very, very similar. Ignore this error down here, by the way. OK, so it's going to go. All right. So this little button, it looks like a little guy jumping over, says execute that line, but don't go inside the function that's on. The one next to it says execute the line and go into the function if it happens to be a function call. But anyway, so then you can step through the program one line at a time and look exactly at what's going on. Okay? In fact, because we did this earlier, here's the for loop we stopped at. If I say, let's see, let me make this a little bigger. If I get rid of the breakpoint there and say continue, it will go back to the for loop again. Oop. Oh, no, there's another line there. It will go back to the for loop again at the beginning. And now it's iteration 2. Or 1, really. OK? And then anyway, if you want to go into this and do the next line in the for loop down here, you would hit this one. And see how it goes down there? And then the next one goes there, and then the next one goes there, and the next one goes there, et cetera.
Wait, then what does step into do?
Step into, if there was a function, step into goes into the function and runs the function one line at a time. Okay? Yeah.
So if you have a program that reads in data, like
Yes.
from a file or from the console, and the way the
You're reading in
flow,
files.
and if the flow of the program depends on the input, like you might end up using a function or not depending on what gets input.
Yeah.
Then is there a way that the debugger can anticipate that?
No, the debugger can't anticipate it. You have to kind of anticipate it. What you would do is put a breakpoint inside the function. If it doesn't get called, it means that function never got called. That's how it knows. Now the debugger's not super smart. I mean, it basically just runs, and then if there's a breakpoint, it says stop. That's all it knows.
But can it run based on a certain time?
You have to put a little more logic into that. It's a little tricky to do that, but you just have to put I would put an if statement in there yourself if you need, and then put the breakpoint inside the if statement. I can talk more about that. It's getting a little more into the weeds than you probably need to know right now. Yeah. Okay. All right. Good. Debugging. That's kind of a basic idea of how debugging works. Okay, I just wanted to show you that you can see lots of program state, and it will help you when you're debugging like your linked lists and things. Okay. All right. There we go. Okay. All right. I mentioned this the other day. Obfuscated C. Take a look what I have up here on the screen. So you see that black box there with all those characters in it? I don't know if I zoom in a bit, can you see the thing that says pound include stioh.h, blah, blah, blah? Pound define, and you can see some more defines in here and so forth, right? And there's all this. That is C code that is legitimate. Like you can run this through a make file, or run it through make, and it will compile this program. And the guy who wrote it made it up to look like fluid, right? And you go, oh, that's kind of clever. He made it. I have no idea what the program does, right? Well, let's take a look at what the program does. Okay, hopefully this. Whoa, whoa, whoa! Yeah, hold on. That was like the loudest thing I've ever heard. Hold on. Where's the video? Where's the? Let's see if that. Hang on. See if that one works, and maybe. Hang on. Sorry for that. I can't do it on the computer. There we go. No, you can't actually. No, it doesn't. It's through the HDMI. So here's what's going on. I want to pause this so I get the sound a little bit up higher. I think that's the right button. There we go. They're compiling this right now, and they're going to make the file right now, and it's going to compile this program, and then he's going to run the program. And in fact, what he does is he runs the program on the program. In other words, he inputs this program into the program. It's a very kind of recursive sort of thing. But he's going to run the program and take as input the program text. Okay? And let me blow this up a little bit, and let me show you what actually happens. Okay. And then he's going to pipe it into this thing. This is a fluid simulation. It's a fluid simulation on the input on the actual program. Right? Okay, and it just keeps going here for a little bit. There we go. Keeps going for a little bit. And then there's some other files like column.txt. And he pipes in column.txt, and oh, there's more fluid thing, right? This is a generic fluid simulator written in C that you can't even understand, right? I think the comment by the guy who wrote this was, yeah, I spent a long time on it. I don't think my wife's ever going to talk to me again. Right? This one's a neat one, too.
Oh my god. So I take it it's an endlessly looping program?
It's an endlessly looping program, I think, yeah. And it just keeps going on. Right? And it's just, what's that?
Is it actually like physically correct?
It's, well, you can tell there's some things spitting out the sides that it's not correct, but it looks pretty good to me. I mean, it looks like a fluid might behave that way. I mean, the guy in his thing talks about the fact that he had to write all the code to physically make it do the right thing. But I mean, once he gets it written, he can have any of these things in here. I believe that like these characters are the wall, and this is it has to have those characters in there, but kind of neat altogether, right? Yeah, and so this guy won the contest, I think, a couple years ago. This one's a neat one. Clock's a neat one, right? Just a little hourglass that you can sell some sand spit out, but still kind of neat, right? Okay, so that's that one. This goes on for a while. Let me see what I can do. Okay, what's that?
Did he write the code regular and then turn it into like after?
I'm almost certain he wrote the code regular and turned it into obfuscated code later. Yeah, he actually de-obfuscated it if you want. But here's the last one. He just did it again in color though, right? Which is the same exact thing, but it just adds all sorts of, adds colors to this. So pretty neat stuff, huh? And this is all because this guy, figured out how to do this, and he wrote a program. And remember, his program was this long, it would fit on one screen, the whole program. That was the whole program, right? That does all this. So it's amazing. If you guys want to get into hacking and stuff, this is the kind of cool stuff, right? Okay, neat stuff. There's but your code can't look like this, okay? Not now. Submit it to the conference or the competition if you want. The other one was so everybody, you guys know I'm in the Navy, and you ever see, I don't know, something they do in some old movies where they have the guys on Navy ships have these flags, 2 flags, and they're signaling between flags locations, right? Well, some guy wrote a little program that the program is on the left up here, and it looks like a little signal flag, and then there's all the little signal flag direction things. Right? What happens is, let me see if I can find this one real quick. Let's see. Am I in there now? It is right here. Okay. Anderson. Okay. If you go in here and then type something in like Tufts, right? You can see there's a little guy there, and he's holding up like a flag like this. That's a T. And then this one's a U, and this one's an F, and this one's a T, and this one's an S, and this one says I'm done with my word. Right? And it can be anything, right? It can be right, supercalifragilistic, whatever, right? Right? So that's that. You know what he won the competition for? What his category was? Best use of flags. Right? Yeah. So I think they made that special category just when they saw this program. But anyway. So yeah. So your code is not allowed to look like that, but you can do fun stuff with C and with code like this. Okay. All right, let's move on. Okay, let's start talking about algorithm analysis here. The question is, how do you go about comparing algorithms or programs so that you can make these big decisions we've been talking about all along, okay? This program right here is the Array Max program, slide number 7. This is the Array Max program, and it basically does what? Can anybody want to look through that? I'm not going to. Don't worry. You should be able to read code and figure out what it does, like small, simple samples like this. But can anybody tell what this is doing? Let's give everybody 30 seconds to look at it. Who thinks they know what it's doing? A couple people. Okay, yeah.
It's finding the max number in the array.
It's finding the maximum number in an array, right? That's what it's doing. It's going through the array, one value at a time, and it starts out by saying, hey, I'm going to set my current maximum to the first value, because guess what? If you're going to start with anything, you might as well start with the first one. And then it loops through, the for loop loops through and checks all the other values, and then sets the value to the current max if it is the current maximum, and then it goes all the way through and then returns the current max. What if the first value was the maximum? Does this program stop in the middle and say that's the maximum? Yeah.
No, it would just loop through it the whole time and say, nope.
Is it possible to do that? To make it so that it stops after it finds the maximum? If it's sorted, yes. Right? If it happens to be sorted, sure. But you have to know that. This all goes back to the information part that we're talking about, right? But in this case, let's say we don't know. You have to go through the whole thing. Okay? All right. So we want to analyze this program. Okay? We want to look at it. We want to say, hey, what does this how fast is this program going to go? Right? How fast is it going to go? And what I mean by that is, well, I could mean lots of things. But I mean, in general, how fast is it going to go? Like, if we can come up with some general idea for describing this algorithm that we can compare to other algorithms, then we're going to be in good shape. Okay? So we could do the following. We could code the algorithm up, which we did, determine for every instruction how much time it takes to run that instruction. Okay? And in that case, you guys should probably know this, but your C code gets compiled into assembly code, which is basically machine code, which is what the underlying processor knows how to do, and it runs like one operation at a time, right? Your for loop could be like 7 or 8 different operations, like of the start of the for loop, just to get into the for loop. But what we could do is we could do that, we could turn it into assembly code, and we could count every time an instruction runs, and we could see how long it takes, and then we could determine how many times, how long it takes, and then we could add all those times up and find the running time. We should be able to do that, at least for the most part, right? Now, it depends on what else is running on your computer and what else is going on, but for the most part, we can do that. Well, this whole like turning it into assembly language part, let me show you what the assembly language code looks like for this program. Oh boy. All right. This is like the low-level stuff. And if you get into some other classes, you will do some assembly language programming. Comp 40, you do some assembly language programming. But you don't really want to spend too much of your time doing this, right? I mean, some people do, and some people love it, and that's great, right? But look, it kind of, after a while reading this stuff, your eyes start to bleed a little, right? Because it's kind of intense reading this stuff. It's not a nice fancy for loop, right? And even though they tell you stuff like, hey, you're in the loop and whatever, you don't want to have to count all this up. And we do not want to have to do this for all the machine languages, okay? We want a much more general approach. Okay? And if you find yourself ever having to read a lot of assembly code, you'll see what I mean in that case. So we don't really want to do that. We don't want to add up every single little piece of the program, okay? Like every instruction. You could do that, but that's not really the best way to go about it. Waste a lot of time doing that. Okay? That would work, but it's complicated. And especially it's complicated because today's machines, your compilers optimize everything. Okay? So you might write a program, and then optimize some things and count all those things and be wrong because the next time you optimize a slightly different way and it counts differently. So we're just not going to go down that road. Okay? It's not really the best way to do it. Instead, what we do, okay, we're on slide 10 here. Instead, we're going to define what we call primitive operations. Okay? And a primitive operation, well, these are some examples of primitive operations. But basically, they are a part of the code that can be compartmentalized. In other words, we're going to take this little part of the code, and we're going to say that part of the code takes 1 to do. And by 1, notice I didn't say 1 second or 1 hour or 1 minute. It takes 1 whatever you care to use as your time. It's going to take 1 to do it. Okay, I'll show you an example of that in a second. But how fast is your computer? How fast is the computer like right here on my desk? Any ideas? Like the clock speed? Yeah.
Most modern high-end laptops are what, 2.4 gigahertz?
I don't know. Let's see what mine is here. Mine's relatively, mine's 2.8. So I guess mine's super new, right? 2.8 gigahertz, which is 2.8 times 10 to the giga, which is 9, right? 2.8 times 10 to the 9th hertz. My first computer that I actually used when I was in like high school, I had an IBM PC, a vanilla IBM PC. It ran at 4.88 megahertz, right? Times 10 to the 6th, right? And that means that the computer now is like, what is this? 2.8, let me get out my 1 gigahertz computer in my pocket. All right, hold on. Let's see. If we 2.8 times 10 to the 9th divided by 4.88 times 10 to the 6th, my computer is 573 times slower than the computer on the desk here, right? We do not want, like when I took data structures using that computer, I don't want my algorithmic analysis to be different than using today's computers, okay? The point is, we're going to call a primitive option or a primitive operation one-time unit, whatever that means, in yesterday's computer or today's computer or tomorrow's computer. Yeah?
On those frequencies,
Yeah.
are they binary operations per second?
The frequencies binary operations per second. You're not a double E, are you? Right? No, the frequencies in megahertz are basically how often the clock changes on the processor, which means, at the very kind of basic level, it means that that you can do one thing during that operation, during that clock changing. So sometimes it can be an addition. You might be able to do it in one operation, but multiplication you probably can't do in one operation, right? So, but yeah, in general, that's what that means. Yeah. Okay. So primitive operations. If we assign a value to a variable, we're going to say that's one operation. Okay? It takes one to assign a value to a variable. If you call a function, we're going to say that calling a function takes one time step. Now, people will yell up and down about that. They say, wait a minute. Calling a function, you have to do lots of things. And you may not know anything about what it means to call a function, but you have to do a lot of operations to call a function. In fact, you probably have to do a lot of assigning values to a variable. But guess what? We don't care. Right? We care. We're going to say, if you're calling a function, you're just going to call it 1. Okay? Arithmetic. If you're adding two numbers, call it 1. If you're multiplying, call it 1, even though it takes longer to multiply in general than to add. Divide, same thing. Call it one operation. If we compare two numbers, if you say if x equals y, one operation. Okay, same thing for indexing into an array. X bracket 4, one operation. And then returning from a function, one operation. You kind of get the idea. One operation for all of these things. Ben?
So what wouldn't be a primitive operation?
A for loop is not a primitive operation because the for loop has lots of operations inside it. Now, you probably could say that well, no, you can't really say that a for loop is a primitive operation because it may or may not run the number of times that you think it does and so forth. So things like that are not. But in general, stick to these ones and you'll be okay. And I won't ask you to do this very often for these kinds of things. I'm not going to say list all, well, I might. I guess I could on the mid-year say list the primitive operations, but probably won't. So let's go back to our array max function. Okay? And we're going to look at this array max function, and we're just going to count up all these primitive operations. Okay? Let's start out with the first one, which is current max equals a bracket 0. Okay? How many primitive operations is that? Yeah, it's 2. And those of you who read it and don't know why, don't do that. Why is it 2? What are the two operations? Yeah, go ahead, Mara. Declare a variable, assign a variable. Well, so actually, I guess you could probably count it as 3 because there's one other thing in there. Yeah. Indexing into the A0. So sometimes this is a little bit hazy too, right? So you could count it 3 depending on if you're counting creating the variable. Most of the time in this case, the compiler creates it like as the program loads, so it's not actually new to the program. It doesn't actually count against you in that sense. But again, we're going a little low level here. And if you mix up by 1 or 2 operations, it doesn't actually matter, as it turns out. You'll see why in a minute. OK, but basically, we're going to call this one 2. The assigning A0 to current max is one operation. We're going to say indexing is another one. Fair enough? Yeah.
Doesn't searching for A in the whole memory take time?
Does searching for the array? Yeah, it takes 1. I mean, that's what we're calling it. We're calling it 1. Now, incidentally, when you do an array, the search part is easy because you don't actually search. You directly, like you don't have to go 1 by 1 by 1 by 1 by 1. If you want index 2014, right, you go right, the computer is able to instantly go right to that one and pick it out. It doesn't have to go through and find it. So it takes 1.
What about A itself? Like,
Yeah, right. We're just going to call the whole thing 1. Don't worry about the lower level details in that, because that's getting a little even farther down into details. Okay? And if you called this, if you said, OK, I want more details, I'll call this 5. I don't really care. In the end, it's going to all not matter. But just we're going to say it's 1 for now. OK? All right. Let's see. What's next? We've got the for loop. In the for loop, there's actually 3 things going on in the for loop. You've got the int I equals 1, right? That actually happens just once. Because at the top of the for loop, it initializes the variable I to be equal to 1. Okay? All right. And then you go and you say, this is actually a test, remember. In a for loop, this is a test saying, if I is less than n, keep going in the loop, right? And then that happens, how many times during the loop do you do that check? N times, right? Right? You have to look at it n times. You have to say, OK.
Well, n minus 5, right?
N minus, no, n times.
N plus 1.
Yeah. Is it n plus 1?
It has to run the time that it fails.
It does have to run the time that, but then you know what? It's a less than, so it is only n. As it turns out, it's only n. Yeah. Yeah, question?
Yeah, that's it.
Yeah, so it actually runs n times. OK, now, again, if you said it was n plus 1, I don't really care. It doesn't matter. Right? In this case, it's not going to matter. You'll see why in a little bit. OK, but it runs n times. And that's the meat of this problem, right? You have to run this n amount of times. And there's no way getting around it, because we already said that we don't know if we've hit the maximum yet until we've looked at all of them. OK? All right. The I++ happens n minus 1 times, because exactly what you were saying. The last time, it actually doesn't happen because you don't increment on that last one. Once you've checked for I being less than n and I is no longer less than n, you don't increment. So that one actually does n minus 1 times. If you said n times, I'm probably not going to care. OK? But for a total, this whole line here runs a total of 2 n minus 1 operations. OK? The whole line. That's how many operations. I think I did the math right on that one. OK?
Wouldn't the check happen one more time?
No, the check happens one extra time, right? Which is that's where the n minus 1 part comes in. It happens n times because you're less than, and then the n minus 1 is the other one. So n minus 1 times. I believe that's right. If it's off by 1, again, I don't really care in the end, but for now, let's leave it at that. OK? All right, let's keep going. This is a lot of analysis for this one program. I'm just kind of getting you used to doing this. You will not have to do this like often, trust me. You'll start like you'll scan over a program and go, OK, this part's this and this part's this, and you'll see it. You will not do this level of detail. OK. This one, if current max is less than AI. OK. This also happens n minus 1 times because we don't actually check in the first one. Well, I mean, we check in the first one, but we've already gone through the first one. So this happens n minus 1 times. OK? How often do you change the current max? Alan says we don't know, right? Why don't we know? Because who knows what's in the array? If it was an array in order, you would change it every single time. If the first one was the maximum, you would change it never, right? So this is one that we don't really know. Yeah, I had a question.
Yeah, for the current max is less than the AI.
Yeah.
Why is that only one operation and not 2?
Oh, yeah, good question. You're right. This thing could run. You're right. This is going to be a dereference, and this. So I think that's where the 2 comes in there. I think. I think so. Yeah.
Got it.
That's where it comes in there. Yeah. OK. Good call. OK. Keep me honest. OK. And so this one we don't know. This one, the current max equals AI. We don't know how many times, but we know a minimum and a maximum. We know that it could happen 0 times, and it could happen at most 2 times n minus 1, because every time we could have to do that. We would have to reset that one. OK? All right. And finally, for the total loop, we have between, and this is adding all this up. You can do that in your spare time. Adding all this up, 4 times n minus 1 is the minimum amount of times this whole stuff the loop has to run. And the maximum is 6 times n minus 1 if we happen to be in that case where everyone is bigger than the last one. Okay? And then finally, the return we're going to say happens once. Consider that a function call. We'll say it happens once. Yeah?
Is incrementing I 1 off or 2?
We're going to call it 1. If you want to call it 2, fine with me. We can argue all day about how much it is really. Yeah, because you're right. I mean, you could say I equals I plus 1. OK, you got to do, yeah. But for this analysis, 1. If you're worried about it, yeah, that's 1. Right? I mean, it's basically saying, look, this can be 1. Because in the end, you'll see the math says, don't worry about it. Like, in the end, OK? Math teachers would get really mad at me for saying that. But you'll see how it works out in the end. OK, that was a lot of stuff to count up all these operations. OK? A lot of stuff. Here's what it ended up being. Okay? At least for this function, we do at least 2 plus 1, and I'm adding up all the different numbers we had up before. 2 plus 1 plus n plus 4 times n minus 1 plus 1. That's 5n operations. In other words, if our array is 1,000 elements long, we're going to do basically 5,000 time operations, whatever that time operation is. On my 1986 PC, it's going to take a while. On the PC today, it's going to be really fast, but in relative terms, it's the same. It's 5 times the number of operations, or the number of elements in the array. So far, so good? OK. And at most, we're going to do 7n minus 2, because that's that's how many if you had that degenerate case where they were all bigger than the others. Okay, and that's the part where you have to update the index, or you have to update the current max. Oops. OK. So, in other words, the best case for this algorithm, if we had a great algorithm where the first one was the maximum, we would have to do 5n. If the worst case was the last one, or all of them in between were bigger, then we would have 7n minus 2. What's the average case in this? This is a tricky one, right? This is where you get into things like you have to kind of know what types of data you have, right? I mean, if you're doing data where you know that you're going to be, adding times that are faster, 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 or whatever, and then you can figure out, oh, the average is going to be this. It's a very empirical sort of situation in that case. You can't just say, oh, the average is this. You can't just kind of divide it in two and say that's the average. It's not going to work that way. I will generally not ask you to find the average complexity of these because sometimes you can't do it in cases like this, and sometimes it's hard to do because there's a lot of math involved. Take algorithms class, take theory of computation. You'll get into some of the details there. Okay, I'm not going to worry about that right now. Okay, all right. Do we need that much detail? That was a lot of stuff, right? We argued over 2 or 3 operations, whether I++ was this and that and all that. That's a lot of analysis that's detailed that we can argue about, right? We don't. Okay, we don't need that much detail. Okay, what do I mean by that? What I mean is, let's simplify this by doing a much bigger picture of how we're going to go about this. All we need to know, as it turns out, is that array max grows proportionally to n. If you have 1,000 elements in your array, it's going to take 1,000 units of time. If you have 10,000 units, it's going to take 10,000 units of time. And you can argue about whether it takes 10,020 or 10,050 or whatever, but that is all kind of noise, right? You guys have done in science classes significant digits and significant figures. It's kind of the same idea that a lot of those digits at the end aren't going to matter. If it takes 10,027, it's not going to be any different than 10,000 and 10,000. That actually reminds me of one of my favorite jokes, my favorite nerd joke, right? 2 guys walk into the Museum of Science, right? And there's a big giant dinosaur inside the dinosaur skeleton or whatever. They walk into the Museum of Science, and the one guy turns to his buddy and says, "That dinosaur is 1,000,004 years old." And the other guy looks at him and goes, "How do you know it's 1,000,004 years old?" And the guy says, "Well, I was here 4 years ago, and they told me it was 1,000,000 years old." Right? No. Right? No, it is not. It's still 1,000,000 years old, and it'll be 1,000,000 years old for another 500,000 years, right? Okay, so you have to the significant digits are kind of a big deal in this case. So it's the same idea here. We don't care in the broad scheme of things all of that math we just did. You will when you get to algorithms. You will and sometimes they matter when the numbers get the number of times something happens is big enough, it will make a difference, but we will not even care about that in this case. Okay, this is the slide where I said, math people, you have to hide your eyes. Or non-math people, you have to hide your eyes. Okay? Here's what we're talking about here. Okay? What we're talking about is, and this is kind of the definition of this. Oh, did I miss this? Oh, I missed a whole slide. Sorry. You're like, what is it? I don't even know what he's talking about. Let me go back. Okay. What I was just talking about, this idea of doing this broad scheme of analysis, we're calling that big O notation. Some of you guys may have heard of this before. You will see it in lots and lots of CS classes if you keep taking CS classes. You'll see it in some math classes too. but mainly in CS classes. And what this is it's our way of simplifying things, okay? And the O, in this case, I believe stands for on the order of. In other words, this algorithm is going to run on the order of linearly, or n times for n input values. Okay, if you have 1,000 elements, it's going to run 1,000 time units. Okay, that's the kind of simplification we're talking about. Wikipedia says big O notation describes the limiting behavior, key word phrase there, limiting behavior of a function when the argument tends towards a particular value or infinity, usually in terms of simpler functions. What they're saying is, if you were to run this program for a really long time, how would it behave? Okay, based on the inputs and based on the algorithm itself. Okay, over a long time. This is the asymptotic behavior part. You know, asymptotes in math class are like when you get to infinity. Like what happens as you tend towards infinity. Same idea. We're going to tend towards infinity here. All right, this is the math slide. Here's the whole thing about the functions. What this is showing, okay, this is showing, you can read that, but this is showing two functions. One function being this f of n here, right? And this f of n starts out pretty high. There's two functions, f of n and g of n. F of n starts out pretty high, right? What's happening here is, what this means is, you know how when you start up a program, there's some overhead to starting it up. Like you have to call a function, and you have to start the for loop, and you have to, like those little overhead things, that's going to take a little extra time, especially for small programs. For programs that don't have millions of elements in their arrays, the stuff at the beginning is actually going to start to matter a little bit. Right? So the function f, which is the function that we're worried about here, starts out and there's some overhead, which means it's kind of there takes a long running time compared to this other function, which we're calling g of n in this case, which takes a little less time. And all it's saying is, at some point in time, those functions swap. F of n becomes less than g of n forever. Okay? There's no space where f of n goes back up and slips up again. So basically what we're saying is we want to look at this one function f of n, which is basically the description of our algorithm in mathematical terms, and we won't get into those kind of detail level stuff. But we're basically saying, look at the description of our algorithm in mathematical terms, compare it to some other one, and forget about the stuff when the program's really small. Because we don't care about when the program's really small. It's when the program gets bigger and bigger and bigger that we care about. You guys don't care when a program runs in 1 millisecond, right? You care if your program runs for half an hour. Right? Because you've got lots and lots of stuff. The 1 millisecond, it takes more than a millisecond to set up a loop. Right? So that part's all noise. This is the noise part down here. After this, we're good. So we say actually that the function f of n is on the order of, or is order, g of n. Okay, meaning that in this case, like g of n might be linear or something. We could say that f of n is a linear equation. In this case, it might not be linear, but this is just a diagram of what it might look like. But we'll see some more examples of that. Okay, that's the mathy part. Probably the most math we'll do in here. All right, that's that. Questions on that? Yeah.
So f of n is ordered. G of n means that g is going faster.
No, it means that we don't care. G of n is like this kind of nebulous, like we're gonna. Well, it's linear, quadratic, polynomial, logarithmic. You'll hear words like that in the next couple slides. You'll see that. That's what g of n is. We're going to say that f of n behaves logarithmically, or it behaves linearly, or it's on the order of a linear equation, or on the order of a quadratic equation. You'll see what that means in a couple slides. Yeah.
Never mind, sorry.
Okay. Yeah.
It seems like from this definition, anything that grows slower than any other function is on the order.
Yeah, good question. Yep. You can find functions. If you find a function that's between these two, then f of n is actually on order of the other one. These are two very defined functions, and if you, in this case it's g of n, but there might be one in between. So it's not, you have to find the right one. It's not just g of n is like the end all be able. You were absolutely right. Ben?
But wouldn't it also have to start out ahead of the other one first?
No, not necessarily. Oh, it wouldn't have to. No, it just basically. Actually, in fact, that's a very good point. There could be some other function in between here that is actually faster than both of these, right? And then ends up slower than both of them because of the way, the overhead at the beginning and some other issues. Yeah. So, but in the broad scheme, again, don't stress too much about this. I just wanted you to see the kind of the idea. We're going to compare our function and our algorithm to some other function that's well defined in that sense. Okay? All right, you'll see how this works out. The cool thing is, and all of that like last 20 minutes, is that there's a dirty little trick here when you're doing these algorithm analysis problems. And it goes back to the dinosaur and the dinosaur bones being 1,004 years old. This is like the take off the significant figures part, or the insignificant figure part. What we're going to do is we're going to find the biggest factor. If we calculate that there's 7n minus 2 operations, the biggest factor in here, not the biggest number, but the biggest factor in here, okay, is the one that we care about. Anything that's a constant is just going to go away, right? The 2, because it's a constant, is going to go away, right? The n is going to be important, but the 7 is going to go away. So 7n minus 2 actually ends up being on the order of n, because we don't care that there's 2 extra operations at the end. How many times do you return from a function? Once, right? Part of those 2 operations was the returning from the function. We don't care about the 1 operation it takes to return from the function when you're talking about a function that runs for an hour, right? It takes a millisecond to return from the function. We don't even care about that, right? These 2 ones, out. The 7n, 7 times, so if something takes an hour and something takes 7 hours, you think to yourself, well, that's actually a pretty long time. Nope, it's not. Because the next order of magnitude up would be like, instead of 7 hours would be, or let's say it takes, instead of 7 hours, it takes 49 hours, right? It's like a squared function or something like that. We're not going to worry about these constants being 7 times slower. We're going to worry about on the order of, some other factor of n or something like that. Okay? All right. I'm seeing some faces like people are like, I don't know what he's talking about. You'll see. You'll see what this is all about in a second. Okay? All right. Here are the ones we care about. Okay? We're going to care about the following types of functions. There are others, okay, but we're going to care about the following. Constant time functions. Constant time functions do not depend on the input size. Okay, so if you have a function and it takes 1,000 elements or it takes 1,000,000 elements, but you can accomplish whatever your task is without when it doesn't matter that there's 1,000,000 or 1,000, that's called constant time. This is kind of like the holy grail of algorithms. If you can find an algorithm that runs in constant time for some set of functions or for some inputs, you latch onto it. Remember on the first day, anybody remember what the data structure was on the first day that was like super duper great? Hash table, guess what? Constant running for most operations. Okay? So that's the holy grail. Like that's why hash tables are awesome, because they actually get to this like holy grail like situation, okay? And they tend to that anyway. Logarithmic's another really good one. Remember we were talking about breaking a problem into halves, 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 like the binary search where we did the number search? That's a logarithmic problem. Awesome. Okay? You really want to be able to get logarithmic. You can't get constant, which you can't get that often. You can get logarithmic. Great. Yeah? Does the base logarithm matter? Not as far as we're concerned. Good question. We are going to generally be doing base 2. We're going to think about base 2. Logarithm of base 3 and 4 and 5, better. But we're not going to worry. We're not really going to see too many of those cases in this class anyway. Yeah, good question. Linear. That's your standard. If you've got n elements, it's going to take n amount of time. If you've got 10n, it's going to take 10n amount of time. Right? Okay? Yeah?
What's the difference between linear and constant?
Constant says it takes 1 time. Right? If I wanted to count all you guys up, right? And I had to go Moretta and then blah and then blah and blah blah, right? And count everybody, and I have to count everybody. That's n time. If somebody's holding a variable that says how many people are in here, and I look at that variable and it says there's 82 people in here, that's constant time. If I go, oh, it's 82 because I can read that variable, that's constant versus linear. Okay? All right. We've got quadratic time, which is n squared. This starts to get a little ugly. When you talk about n squared behavior, things get slow in a big way. I was going to say they get slow fast, but they get slow in a big way, right? Because, and by the way, linear behavior, or quadratic behavior, unfortunately happens fairly often in computer science. Does anybody have, either sitting in front of them right now, or maybe in your dorm, or maybe somewhere else, anything that's a square shape that you watch things on? Right? Pixels in a monitor are two-dimensional, right? There's 2 dimensions. And if you want to go through all the pixels on a screen, you have to go through all of them in the left-right direction and all of them in the up-down direction. That's inherently an n-squared behavior, because you've got like n this way and n this way. And maybe it's not the same n, but n this way and n that way. That's a two-dimensional problem, which is going to be quadratic. That's why graphics cards are so important for your computer, right? They have gone and they've said, how can we make these things that are quadratic behavior act a lot faster? Right? And the answer, by the way, is to add lots of processors. Your graphics card in your computer these days has lots and lots and lots of individual processors which can deal with individual pixels. And each individual processor, instead of running in n squared, can run either in n or in constant time, and it's better. Okay? So there's those kind of issues that you can think about. Then you get into polynomial time. Polynomial time is kind of even uglier. That's like an n cubed operation, right? So 2-dimensional screens are n squared. Is there anything 3-dimensional that we might want to model? The entire world, right? 3 dimensions. You add a 3rd dimension, all of a sudden you're into the cubic realm, and that's even harder, right? So modeling 3-dimensional things takes time. Why? Because there's 3 dimensions, and you have to all of a sudden do these operations that are cubic and so slow, right? In that sense. Okay? And then finally, we've got these exponential functions. If you ever find yourself writing a function that's exponential, you'd better rethink it, right? Because it's going to take a long time. Anybody ever played the game Tower of Hanoi? I'm going to show you this little thing. It's unfortunately a little flash thing, but the Tower of Hanoi, I'm going to bring this up now, is 3 posts, okay? And what you're supposed to do with these posts, they have discs on them. You played this before? Some of you guys? What you do is you take this. You take the 3 discs, in this case, and you try to get them all over to the 3rd post. And you have to do them such that the biggest one's on the bottom. And you can only move one at a time. And you can never put a smaller one below a bigger one. Right? So watch this. If I do this, if I take the first one, and I always screw this up, even though it's just 3. If I put the first one over there, and then the middle one goes in the middle. And then now the only thing I can do left is move this one. Well, I could move it over here, but I'm going to move it here, I think. And then this one goes all the way over here. And then this one, oh, it's got sound too. Ready? Wow. OK. And then this one goes over here. And then this one finally goes over here. And it should take in 7. All right, it does take 7. OK, so that's the point, right? For 3, it's pretty easy, right? If you all of a sudden go into like 4, instead of taking 7 times, right? Any idea how long it takes? It actually takes, there's 3 disks before, right? 2 to the 3rd is 8. 2 to the 4th is 16. So it actually takes 15 moves. It's 2 to the n minus 1. It takes 15 moves to do 4 of these. I'm not going to demonstrate that. I always screw it up, and it's a pain, and we don't have time, right? You can also do, right, you can do other ones where, and this will let you do up to 8 times, right? And 8 times, what's 2 to the 8th? No, 2 to the 8th is 256, I believe, right? And so this should take 255 moves to do, right? You can actually, in this case, you can actually let it go, and then it will do it for you. But we only went up by a factor of, like we went up by, each time we go up by 1, we go up by a square, right? It'll do this, and it'll do it for you, but it takes forever unless you do fast forward, in which case it goes, right? But it's going to take forever to do this, right? Were there 7 or 8 on there? I forget. Well, anyway, if there were 8, then it's going to take 512 times, right? So no, I'm sorry. No, I was right before, 256. But anyway, the point is that this will go on for a long time, right, to do this. And that's but that is an example of an exponential function, and you don't want to write those if you can help it, right? You do not want to write those if you can help it. Okay? All right. Back to the dirty little trick. Something like this. What's going to take longer time, an n cubed function or an n function? n cubed is going to take much longer, right? So n is what's going to take, and what about log n? Is that a good one or a bad one? That's pretty good, actually. Log is pretty good. N times log n is still not as bad as n cubed. In fact, n times log n is like a good thing. So n times log n is actually better than n cubed. It's also better than n squared. Okay? Not better than n itself, but that's it. But our dirty little trick was, first of all, get rid of all the constants. 20 gone, 10 gone, 5 gone. What's left? The n cubed and the n log n. We said the n cubed is going to be slower. Guess what the order is for this? The order is for this function. N cubed. All the rest of this stuff, don't care about it. That's the significant digits we don't care about. Okay? That's how you do this analysis. If you have functions like this, really pretty simple. Okay? All right, let's look at another one. Nested loops. Nested loops are a loop within a loop, right? We heard you like loops, so we put some loops in your loops, right? And right, yo dog, I guess. And so in this case, for a nested loop, you've got a for loop, and then inside that for loop, you have another for loop. In this case, we're using the same n in both cases. Okay, how are we going to analyze this? How many times does the outer for loop happen? N times, because it goes up to n, on order of. There's other little onesies and twosies we're not going to care about. How often does the inner loop happen? It happens n times for every outer loop. So the total running time here is what? N squared, right? The inner loop is n times. The outer loop is n times. And so the total complexity is n squared. This is your go through the monitor pixels, right? If this was like x values instead of n, and this was y values, you'd be going through all the x values and then doing the x values and then doing a y value for each one. Make sense? Okay. All right. 3 loops, same thing. Cubic, right? Loop inside a loop inside a loop, right? This is the cubic complexity, and it takes forever to run these things, right? For big values of n. Grows exponentially, right? For 10 times as fast, or 10 times many elements, you've got a cubed number, or 10 cubed times the number of. No, I said that wrong. If you've got twice as many, you've got a cube amount of time more. Okay? Yeah.
Yeah. But of course, it's important that they all depend on the same variable, right?
They do, yeah. But we're in general, yes, you're right. And we're in most cases we're going to have the same variable that's going to go through there. You could probably, we might end up with something that's nm complexity if n and m were different. But that's a very good point, Ben. Yeah, good point. OK, I'm going to, because of the time, there's a couple other ones in here. There's searching in here, which is generally linear, right? It's either worst, so best case is instant because you found it. Worst case is you have to look through everything. Binary searching, which is this log n time. I'm going to let you look through this on your own. This code, it's on the slides. This is where we have it each time. We say, what's your number at half, 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 half. Yeah.
When you say having it,
yeah.
Is that the difference between if we went through, we had a pirate array and we counted how many pirates, or just looked at the variable that stores the number of pirates?
No, that's a constant versus linear. But if you were searching for a particular pirate and you knew they were all in order, and you said, am I at pirate A, pirate here? No, it's lower than that. I can go into the middle of that, and then the middle of that, and then the middle of that. We'll talk more about that in a little bit. But the last thing I want to show you, if we had an algorithm that has 1,000 elements, and the log n version runs in 10 nanoseconds, that's really fast. If the 1,000 element version ran in 10 nanoseconds, for the constant it would be 1 nanosecond, super duper fast. Right? 10 nanoseconds for logarithmic. 1 microsecond, still blazingly fast. Quadratic equation, it would be 1 millisecond. Still, you're not going to notice it. Polynomial, it's going to take a second. Right? Exponential, 10 to the 284 years. This is the one that's going to kill you, remember, okay? This does not matter. Now, what if instead of 1,000 elements, we made it, or 1,000 elements that did in 10 milliseconds instead of 1 millisecond? 10 milliseconds, 1 second, 17 minutes all of a sudden. If your logarithmic runs in 10 milliseconds, it's going to be 17 minutes if it's a quadratic equation, right? 694 hours for polynomial. heat death of the universe, if you want to try it, which the other one was too, by the way, but heat death of the universe if you want to do exponential. You will never write, if you write an exponential function, you better rethink it, because unless you're doing something odd where you have to, like the Tower of Hanoi, no two ways about it, you can do that. You have to do that, but it's going to be, you don't want to write these ones. Okay? Last minute questions? All right, homework assignment due Friday. All right, office hours, I will send an email about the extra C++ office hours until Friday.